Hello everyone, I'm Mighty, your hands-on practice assistant. In this session, we'll go through a structural simulation together step by step and follow along with the practice example. In this example, we will perform frequency response analysis using the modal method. Frequency response analysis evaluates how a structure responds to repeated vibration excitation at different excitation frequencies. In other words, it allows us to check how much displacement or stress increases at a specific frequency. Modal frequency response analysis uses the results from the previously performed modal analysis. In the previous tutorial, we reviewed the natural frequencies, mode shapes, and modal mass participation ratios. In this tutorial, we will use that modal information to calculate the response across a frequency range. When the excitation frequency approaches a natural frequency, the structural response can increase significantly. This phenomenon is called resonance. In frequency response analysis, we check how much displacement and stress increase near the resonant frequencies. In summary, modal analysis identifies the natural frequencies of a structure, while modal frequency response analysis uses that modal information to evaluate the response magnitude at each frequency. Next, let's review the conditions for this example. In the previous example, we defined the material, contact, and mass conditions for the monitor and connecting bracket. Then, we performed modal analysis to review the natural frequencies and mode shapes. We also confirmed in the modal result table that the mass participation ratio was greater than 90%. In this example, we will open the completed modal analysis model and continue with modal frequency response analysis. We will use the fixed constraint already applied in the model and apply a vertical vibration acceleration of 1g, which is 9,800 millimeters per second squared. In the results, we will first use the frequency response graph to identify the frequency where the maximum response occurs. Next, review the displacement and stress results at that frequency to evaluate the deformation and possible failure of the monitor and connecting bracket. Now, let's begin the tutorial example. Click Open in the upper left corner and open the modal analysis file from the previous example. Next, let's define the frequency load for frequency response analysis. In the Structural Dynamic Analysis tab, open Frequency Dependency and select Frequency Dependent Nodal Acceleration. Select the excitation node and enter 9,800 millimeters per second squared in the ty direction to apply 1g acceleration in the y direction. In frequency dependency, you can define the magnitude and phase of the excitation for each frequency. In this example, the same 1g excitation is applied across all frequencies, so enter 1 for magnitude. Next, let's create a function to apply damping. Open the damping function creation feature and create a 2% modal damping function. Modal damping is used to reduce excessive response amplification in each mode. Now that the analysis conditions are defined, let's create the analysis case. In the Analysis tab, open Single Analysis and set the solution type to Modal Frequency Response. Enter the analysis case title and open Analysis Control. Apply the modal damping function created earlier. Next, let's define the frequency set. The frequency set defines the frequency points where the response results will be calculated. A denser frequency set reduces the chance of missing peak responses, but it may increase analysis time. The frequency set includes options such as linear, discrete, logarithm, and cluster. Select the appropriate method based on the analysis purpose and frequency range of interest. Select the analysis case. Then click Define Frequency Set in the subcase to open the frequency settings. In this example, we will create 40 points using the logarithm method to review the frequency range where resonance may occur. Finally, check the number of modes used in the analysis from the General tab. Modal frequency response analysis calculates the response based on modal analysis results, so a sufficient number of modes must be included. If the mass participation ratio is below 90%, more modes should be included in the analysis. After reviewing the settings, create the analysis case and run the analysis. the analysis is complete. Let's review the results. First, double-click the result to review the calculated stress and displacement results. Next, let's review the response graph at a specific location. The response graph shows which frequency causes the most sensitive structural response. In the Results tab, click Extract to open the function. Then select the analysis set, result type, and result item. Select all steps and the node for result extraction, then click Table. Right-click in the workspace, select Graph, and click Preview to plot the response graph. In other words, the frequency response graph is used to identify the maximum response frequency and review the dynamic characteristics of the structure. How was today's lecture? Simulation may seem difficult at first, but if you follow the steps and practice hands-on, you can get started with confidence. With MIDAS NFX, learn the fundamentals one step at a time and challenge yourself with a variety of simulation examples. Then, see you again in the next video. This has been Mighty, your hands-on practice assistant.